In this video, you saw problem 9.92 from the book Thermodynamics Cengel 9th edition. Here the statement of the problem 9. Air is used as the working fluid in a simple ideal Brayton cycle that has a pressure ratio of 12, compressor inlet temperatures of 300 Kelvin and a turbine inlet temperatures of 1000 Kelvin. Determine the required mass flow rate of air for a net power output of 70 megawatt. Assuming both the compressor and turbine have an isentropic efficiency of 100% and 85%, assume constant specific heats at room temperatures. These are the answers that must be matched when we are solving. This is a simple schematic diagram of the Brayton cycle. First is the isentropic compression is taken place in this compressor, and it will require some work input in order to compress the air, and then it is sent to the combustion chamber where heat addition is taken place, and then it is expanded in the gas turbine and it will give you the work output, and the net work output will be the difference of W out minus W in, and then the gases that is coming out from this gas turbine is sent to the heat exchanger where it gives heat out to the surrounding, and in this way the cycle is completed and it is continuous. Let me draw the TS diagram of the Brayton cycle. From 1 to 2 it is isentropic compression. Then this compressor is taken place and it will require some work input during this process. This is isentropic compression and it is a TS diagram. Remember, since it is isentropic compression, then the entropy during this compression must be the same. So 1 to 2, the entropy will be same, that is S1, let's say. And then in this heat exchanger, heat addition is taken place at a constant pressure, Qn 2 to 3. Then again in turbine isentropic expansion is taken place and it will give you the work output. Here you need to provide work input during the isentropic compression 3 to 4. Then finally 4 to 1 is constant pressure heat rejection is taken place. The entropy during isentropic expansions in the turbine is also the same, that is S3. So it means that S1 is equal to S2 and S3 is equal to S4. Let me draw the PV diagram of the Brayton cycle also, that you can clearly understand the data that is provided in the statement, and you will clearly observe and notice what kind of temperatures and pressures are given when you already draw the PV and TS diagram of the Brayton cycle. Starting again from 1 to 2, that is isentropic compression. 1 to 2 is isentropic compression. Then process 2 to 3 is constant pressure heat addition process. It's a PV diagram. The pressure at 2 and 3 must be the same. Here heat addition is taken place, Qn. Here work input is required in order to run the compressor, and then isentropic expansion in the turbine. It will give you the work output 3 to 4, and then finally 4 to 1 is a constant pressure heat rejection process. Remember, the pressure here is P2, that must be equal to P3. Here the pressure is P1, that must be equal to P4, because 4 to 1 and 2 to 3 is taken. So these are the TS and PV diagram of the Brayton cycle. I hope you understand. If still there any confusion in the TS and PV diagram of the Brayton cycles, you can ask in the comment sections. Now it will be very easy to pick what kind of data in the statement is given. Now just simply come towards the statement. Pressure ratio is 12. So the pressure ratio is denoted by ARP, and it is the higher pressure divided by lower pressures, P2 divided by P1. And it is also equal to P3 divided by P4, and that is equal to 12. So that's why I'm saying that before starting the problem, you must familiar with the concept of TS and PV diagram, so you can clearly pick what kind of data is given to you. Inlet temperatures T1, that is 300 Kelvin, and the turbine inlet temperatures is 1000 Kelvin. That means it is T. That's why T3 is higher value in the TS diagram, is 1000 Kelvin. You need to calculate the mass flow rate when it produces a net power output of 70 megawatt. The net power output is equal to 70 megawatt. So if you convert that megawatt into kilowatt, multiply with 1000, so it becomes 70,000 kilowatt. So there's two cases given. In first case, when the turbine and compressors have 100% isentropic, and in the second case it is 85% isentropic. In actual process, it is not 100% isentropic, it is almost less than 100% isentropic. So this 85% isentropic is almost near towards our real applications. In first case, When isentropic efficiency is 100%, we need to calculate the mass flow rate, and in the second case, and the isentropic efficiency is 85%. Now come toward its solution. Consider the process 1 to 2, that is isentropic compressions. Then we can say that T2S divided by T1 is equal to P2 divided by P1 to the power gamma minus 1 divided by gamma. Remember, gamma value is 1.4 and the Cp value for air is 1.005 kilojoule per kg. T1 times the pressure ratio Rp into gamma minus 1 divided by gamma. Now just simply enter the value and you will get the T2S value when you solve it on calculator. I'm just entering the value. And you solve this on calculator, you will get 610.2 Kelvin. Now consider the process 3 to 4 in which isentropic expansion is taken place. That is the turbine. It will give you the work out. Then we can say that P4S divided by T3 is equal to P4 divided by P3 to the power gamma minus 1 divided by gamma. You know that P3 divided by P4 is, so you already know that P3 divided by P4 is the pressure ratio. Then P4 where P3 will be reciprocal of this pressure ratio. So I can write here like 1 over Rp. Now just simply enter the value. Let's solve this on calculators and it will give you the value of P4S, and that is 491.65. Next we need to find the work input that is required to run the compressor isentropically. That is equal to Cp, change in temperatures from T1 to T3, T1 to T2. The value of Cp is 1.005, T2 is 610.2. After solving this, you will get the work input that is required to run the compressor isentropically, 311.75 kilojoule per kg, and the work output that is produced by the turbine After solving this on calculators, it will give you the work output produced by the turbine, that is 510.85 kilojoule per kg. Next, we need to find the net work produced during this Brayton cycle, and it is equal to W out minus W in. So we also know that the net work produced multiplied with mass flow rate will give you the net power produced. Just simply put the values. W net is 199.1 kilojoule per kg multiplied with mass flow rate that we need to calculate in the first case when isentropic efficiency is 100%. And we have given the net power produced, that is 70,000 kilowatt. Divide both sides with 199.1 and you solve this on calculator. It will give you the mass flow rate value in the first case, that is 352 kg per second. Remember, as I already told you, that the first case is ideal one, so in that case it required less mass flow rate of air, while in the second case it is near to the real application, so it will require maximum mass flow rate of air. In the second case, when the isentropic efficiency is 85%, mean the isentropic efficiency of compressor is 0.85 and isentropic efficiency of turbine is given, that is 0.85. In case of compressor, the isentropic efficiency is equal to isentropic work input divided by actual work input. I will represent the actual terms by writing A on its top. So the actual work input will be equal to isentropic work input divided by isentropic efficiency of the compressor. After solve this on calculator, you will get the actual work input of the compressor, that is 366.76 kilojoule per kg. Similarly, in case of turbine, the isentropic efficiency is equal to actual work output divided by isentropic work output. Then the actual work output is equal to isentropic efficiency times multiplied with isentropic work output. Then the net actual work output we need to calculate the mass flow rate in the second case when the isentropic efficiency is 85%, and the mass flow rate multiplied with net actual work output and the net power produced. Is dot on the top represent the power, that is 67.5, and the net power produced is given, that is 70,000 kilowatt. After solving this on calculator, it will give you the mass flow rate 1037 kg per second. As I already mentioned you that in the first case we will require less mass flow rate, while in the second case we will require more mass flow rate, because this is near to the real applications and this is near this is ideal applications. That's why. I hope you understand. If still there any confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed. Thank you so much.